start, Abhijit.
Okay. Hello, everyone. Welcome to the morning session of the 5th day of the Indian Stings meeting. Today in the morning, we will have 3 talks, half an hour each. First by Akshay Yelleshpur, second by Koushik Ray, third by Arnab Rudra. So each of the talk, we will roughly split as 25 minutes for the talk and 5 minutes for the questions. So please interrupt if you have urgent and short questions. Otherwise, let's keep the questions towards the end of the talk in the allotted time for 5 minutes. Okay, with that out of the way, let me welcome Akshay Yelleshpur from Brown University. And he's going to tell us about deformed W algebras in celestial holography. Over to you, Akshay.
Thank you. Can you all see my screen?
Yes.
Okay. Yeah, first let me start off by thanking the organizers for putting together this conference and for giving me the opportunity to speak. It's really a pleasure to be able to join by Zoom. I'm going to talk about this paper that I wrote recently. This is work done in collaboration with 𝗰𝗵𝗶𝗶 and Yicheng Ren, who are graduate students here at Brown, and Professor Anastasia Volovich. To start off with, holography tells us to look for non-gravitational theories living on boundaries of space-times. So for the particular case of asymptotically flat space-time, this would mean the boundary at null infinity. And I'm sure you heard about this in greater detail in Laura's talk a few days ago. But the null infinity of asymptotically space-time has the structure of R cross S2. And it is this S2 which is commonly referred to as the celestial sphere. And there's also another fact that the 3+1 dimensional Lorentz group on the bulk acts as the global conformal group on this celestial sphere. So there's often a statement made that the S matrix is the only observable in quantum gravity. Whether you like it or not, it's definitely a good idea to look for a dual theory which reproduces the S matrix in flat space or in asymptotically flat space. And this has indeed been the driving force for many of us who've been working on scattering amplitudes in one form or another. Specifically, the proposal of celestial holography aims to construct a conformal field theory which lives on the celestial sphere. And this is called the celestial conformal field theory, or CCFT for short. And it has been known for a while now that the properties of scattering amplitudes in the deep infrared severely constrain the CCFT. And very early indications of this was that the soft gluon and graviton theorems that have been known for decades in the bulk, they are equivalent to certain Ward identities of the CCFT. But this was only the tip of the iceberg. There are more recent results. There's an infinite tower of these soft currents, and it has been shown that they actually form a symmetry algebra. So the focus of my talk today will be this infinite dimensional symmetry algebra. And of course, most of this work was done at the classical level, and it's important to understand the effects of loops and higher dimension operators. I won't have much to say about loops in this talk, but I'll talk to you about some recent progress on understanding the effects of higher dimension operators. And we'll see that they constrain the spectrum of the bulk theory in certain ways. So here's the outline of the talk. I'll quickly review what celestial amplitudes are. I'll show you how we can use properties of amplitudes to obtain OPEs in the CCFT. I'll talk about conformally soft limits, which are related to the usual well-known soft limits. And finally, I'll put these two together to show you how this forms a new symmetry algebra. And then I will talk about deformations of these symmetry algebras and the constraint that they impose on the bulk. Okay. So let's begin. The scattering amplitudes are usually labeled by momenta and spins of the particles involved. Now I can think of the scattering amplitude as a 4 vector, or equivalently, I can think of it as a 2 by 2 matrix. Now, the determinant of this matrix is the norm squared of this vector. So for null momentum, I can decompose the 2 by 2 matrix as a product of two column vectors. And these column vectors, lambda alpha, lambda tilde alpha dot, are called spinor helicity variables. Now, this decomposition is, of course, not unique. I can rescale lambda, lambda tilde by opposite phases, and this still leaves the momentum invariant. I can use this redundancy to further parameterize lambda and lambda tilde in terms of an energy, omega, and a coordinate z, which points a direction of picks a direction of the null momentum. And this is also happens to be a point on the celestial sphere. Now this epsilon is just plus or minus 1 and tells you whether the particle is incoming or outgoing. Now the Lorentz group of the bulk acts as SL2C, acts as the group SL2C on the indices alpha and alpha dot. And we can use this to work out how omega and z bar transform under the Lorentz group. And what we find is that omega transforms into this scaling and z transforms under as a Mobius transformation. The way we usually construct scattering amplitudes, we take these one particle states, which are labeled by an energy, z bar, and helicity. I'm using S here for helicity for reasons that will become obvious later. And there's a good reason we use these states. These are eigenstates of momentum, and they make the translation invariance of the amplitude manifest. However, if you're looking at a conformal field theory, these states don't transform nicely under conformal transformation. Indeed, you can see here that omega picks up this extra factor. But we can make this better. We can define a superposition of these states, and this is nothing but the Mellin transform with respect to the energy. And these new states, I will call them as conformal primaries, and we can easily see that they actually transform well under conformal transformations. This is because omega transforms this way, but I've integrated over omega, and I can just redefine the variable to scale out this overall factor. So I can now instead label my states by a conformal dimension delta and a direction on the celestial sphere as well as the spin. So in particular, if I use the Mellin transform for the in and out states of the amplitude, I get a new object. And this is what is referred to as the celestial amplitude. This is basically the Mellin transform of the usual momentum space amplitude. And by construction, this new object transforms as the correlation function of n primary operators having spins Si and conformal dimensions delta I. At this stage, I can already point out a difference between flat space holography and ATS-CFT. The dimensions delta I are not related to any property of the bulk. But I can identify the celestial amplitude with this correlation function of n operators, which have conformal weights hi and hi bar related to the conformal dimensions and spins. And the claim or the conjecture is that there is a conformal field theory which lives on the celestial sphere. This is called the celestial conformal field theory, which computes these correlation functions. And if I knew what this conformal field theory was, I just had to compute the correlation function, and that would and inverse Mellin transform it to get the amplitudes in momentum space. Of course, we are still very far away from actually knowing an example of a celestial CFT. And I'd like to tell you why it is so. You might think, oh, I know 3 and 4 particle scattering amplitudes. I can just compute the 3 and 4 point function in the CFT, and I'm more than halfway there. Well, it's not so simple because I can Mellin transform the 3 and 4 point scattering amplitudes, but the resulting celestial CFT correlators are distributional. So there are these delta functions for the 3 point amplitude. I get delta functions of z bar. For the 4 point function, I get a delta function of the cross ratios. this forces the cross ratio to lie on a circle. However, all is not lost. We can still use many properties of the scattering amplitudes to deduce properties of the CCFT correlators and also about the spectrum of the CCFT. And in particular, I'm going to be talking about collinear limits of amplitudes and soft limits. So let's first look at collinear limits. Scattering amplitudes have well-defined collinear limits. If I look at the dot product P1 dot P2, you can see that the momenta are collinear whenever the point Z1 approaches Z2 or Z1 bar approaches Z2 bar. So if you're thinking of this as in terms of the celestial sphere, the points Z1 and 2 approach each other. So it's natural to expect that this limit has something to do with the OPE. And let's start with the amplitude itself. I have an n particle amplitude. I know that in the collinear limit, it factorizes. In particular, this is true at tree level. In particular, it factorizes into a 3 particle amplitude times n-1 particle amplitude. And this is the picture, and this is the same written in equations. Now I can obtain the celestial analog of this just by Mellin transforming both sides. So the collinear limit is reached by parameterizing the energies in terms of a variable t and also a common energy omega. The only thing I need here is the 3 particle amplitude on the right hand side. I'm assuming, of course, that the exchange particle with momentum p is massless. So this is a 3 particle amplitude involving all massless particles, and it's completely fixed, uniquely fixed by Poincare invariance. So throughout the talk, all of these objects without the tildes on them are momentum space amplitudes, and if they have a tilde on them, they're celestial amplitudes. So the 3 particle amplitude in momentum space is completely fixed by Poincare. So let's begin. The Mellin transform of the left-hand side is nothing but the endpoint celestial amplitude. Now we can look at the right-hand side. Well, it almost looks like it's related to the n-1 celestial amplitude, but not quite, because the variable z bar 2 is shifted by some amount. But I can always just Taylor expand. When I perform the Taylor expansion, I can do the remaining integral over t, and the expression that I get, I've written down here. Now, let's back up for a second. What we did was we started with the endpoint correlator, which was the endpoint celestial amplitude, and we took this limit where Z1 approaches Z2, and I was able to rewrite it as n-1 point correlators, where I replaced operator 1 and 2 by some operator with a different conformal dimension at the point 2. Now, this is exactly what the OPE is. I can now strip off the remaining operators in the correlation function. I can clean up some of the variables, and I can just rewrite the whole thing like so. And you notice there was a beta function here, b of the conformal dimensions, and that is in the OPE coefficient, C alpha p. So now I'd like to talk about some features of this OPE. You can notice that the OPE coefficient is a beta function, which means it has a pole whenever either of its arguments is a negative integer, or 0 or a negative integer. If you're specializing to the case of Yang-Mills, S1 and S2 is 1 and P is 0, this means that the OPE coefficient has poles at delta 1, delta 2 being 1, 0, -1, and so on. And this contribution that you see here, labeled by P, is a contribution from a specific 3-point amplitude in the bulk. And that is reflected in the fact that there is a specific coupling constant here, kappa S1, S2, and P plus 1 minus S1 minus S2. This is the coupling constant of the 3-point amplitude of 3 massless particles with spins or helicities S1, S2, and this. So every massless amplitude in the bulk contributes to the OPE coefficient. But the good news is that there are only a finite number of interactions in the bulk. This is if you're ignoring the existence of massless higher spins. There are only a finite number of interactions in the bulk, and there are only a finite number of singularities that can arise in the OPE. But let's also focus on, for the moment, let's focus on the poles that the OPE coefficient has. And let us try to understand where they come from. And this leads us to the other kinds of special behavior amplitude, which is soft limits. So any tree amplitude can be expanded in a Laurent series around one of the particles, let's say omega-1. The soft theorem tells us that the leading divergence at low energies is 1 over omega. And beyond that, there are no, that's the leading divergence, and the rest are just polynomials or positive powers. So now I want to look at the behavior of the celestial amplitude as delta approaches an integer value k. And this must vanish unless the celestial amplitude itself has a pole here. And indeed, we can exchange the limit and the order of integration to see that this can actually be written as a residue of omega-1 to the minus k times the amplitude. And it picks out a specific coefficient in this Laurent expansion. So this tells me that the celestial amplitude itself has poles at these specific values, k equals 1, 0, minus 1, minus 2. And these are called the conformally soft limits, specifically because k equals 1 picks out the coefficient of the leading divergence, and k equals 0 is the subleading divergence. Now, clearly there are an infinite number of poles, and the residues of the operators on these poles form currents or behave as currents in correlation functions. And now the route towards these current algebras is clear. We start with the OPE that I derived. I take the residue on these poles. That gives me the OPE of these soft currents. And then I can look at the algebra found by their modes. So that's what I'm going to do. I define these soft currents to be the limit where the conformal dimensions take on these specific integer values k, which is 1, 0, minus 1, minus 2. And let me work out the OPE when both of these operators are these soft operators. So let me restrict to the case of pure Einstein gravity, which means the only 3-point amplitude in the bulk is this amplitude coupling 2 positive helicity gravitons to the negative helicity gravitons. This is the MHV amplitude in the bulk. So there's only one coupling constant which appears on the right-hand side, and the OPE can be written in this form. Now I can extend this by adding other interactions in the bulk. Particularly, I can turn on an R-cube interaction, and the effect of this is that it introduces a new 3-point amplitude coupling 3 positive helicity gravitons, and that is the coupling constant you see here, and it introduces a completely new singularity in the OPE. And the claim now is that the modes of these currents form a symmetry algebra, and the path from OPEs to symmetry algebras is quite well known in CFDs. I won't spend too much time on this, but the basic strategy is I take these currents, I mode expand them. The modes can be written as contour integrals of the current itself. Now I could go ahead and compute the OPE. I could compute the commutator of these objects, which I call H. But with my hindsight, I know that rescaling them in a specific way produces a much simpler result. So rather than compute the commutator of H, I will compute the commutator of W. And the commutator can be written in terms of these contour integrals, multiplying over the product of these two operators. I can now use the OPE, and the Z1 integral in particular will pick out the pole of the OPE. And when I do the computation, the resulting commutator looks like this, where N has this rather complicated structure. But of course, if this object has to be a symmetry algebra, it must satisfy the Jacobi identity. And so let's again go term by term. Let's start with pure Einstein gravity. Again, there's only one 3-point amplitude in the bulk, and the resulting algebra was computed a couple of months ago by Andy Strominger. And this algebra is the structure of this algebra is well known. This is known to be the little W infinity algebra, and this algebra has been studied quite long ago. And it turns out that there's no issue with this. You can check that it satisfies the Jacobi identity. But we're interested in what happens if we turn on higher derivative, higher dimensional interactions. In particular, we again consider the R-cube interaction, and the extra term in the OPE that I introduced here will again contribute to the integral, will again contribute to the commutator, and I pick up another contribution. However, if I now try to check if the Jacobi identity is satisfied, it turns out that that is not. It's just flat out non-zero. But this is not too bad, because as I told you, there are only a finite number of interactions that can contribute, and it's possible to check whether we can add extra terms or extra amplitudes in the bulk, which makes the commutator vanish. And for this specific case, it turns out that the only combination that works is if I add a scalar in the bulk. And in particular, I add an amplitude which couples to gravitons in the scalar. This would be like an R² phi interaction. And this couples to scalars and graviton. This is like an R phi squared interaction. And I can compute the resulting commutator. And it turns out that the Jacobi identity is satisfied only if the coupling constants satisfy these specific relations. Now, you can immediately see that if I turned off these interactions, I would go back to the previous case, and all of these commutators, all of these constraints are trivially satisfied. But with these higher dimension operators, these commutators are not the Jacobi identity is not easily satisfied.
Hello, Akshay. Sorry
Yes.
to disturb. You are 20 minutes into the talk, just to let you know.
Yes, I'm almost done. Thank you.
Okay, sure.
And it turns out that if we include gluons into the mix, we get a lot more constraints, not only on the coupling constants, but also on the kinds of particles you can actually have in the bulk. And so, yeah, this brings me to the end of the talk. We've showed that the behavior of the amplitudes in the IR constrains the CCFT. In particular, minimally coupled Einstein-Young-Mills and Einstein gravity and Young-Mills enjoy an infinite dimensional symmetry, which is called W1 plus infinity. The situation is not so clear when we deform these theories. The symmetry is deformed by high dimensional operators, and if we demand that the resulting algebra is still satisfied, that it still obeys the Jacobi identity, we end up with constraints on the coupling constants as well as the spectrum of the theory. Now, the natural question to ask is these constraints, is there any theory which actually satisfies these constraints? or what are other kinds of theories which satisfy these constraints? And also, ultimately, what happens when we take loop corrections into account, and if these constraints still remain to be true, or do they get modified in some way? Yeah. Thank you.
Thank you very much, Akshay, for a very clear, interesting talk. So you did very well on time. We have some time for questions. So Loga, go ahead, please.
Hi. Thanks for the talk. So there are some things I did not quite understand. So these kappas that with these three coefficients that that you were talking about. So you are constraining them. So do you understand that right? That they have not been like computed in any realistic theory. Let's say some low energy limit of string theory or something. Is that right? Has it not been computed in any of these theories, any higher derivative?
Well, these kappas are just the coupling constants of the 3-point amplitudes.
Okay.
So, if you're asking, is this relation satisfied in any low energy effective action of string theory? That's something we still have to check.
Okay.
But as of now, it doesn't seem like it's a very easily satisfied constraint. We haven't checked, for example, we haven't checked bosonic string theory, but we have checked, we managed to find that conformal supergravities for some reason satisfies these constraints. So we're still trying to figure out whether this is a generic feature or this is something very special.
Maybe let me just ask a simple question. Let's say you have a Yang-Mills theory coupled to some matter, some scalar matter, let's say fundamental scalar matter. Do you have constraints for them? I mean, this was all for gravitons.
If you just have Yang-Mills and matter, then there are no constraints. Okay. But if you introduce F-cube interactions, then you find that there are constraints relating the coupling constant of the F-cube term and the scalar couplings.
Yeah, this is a bit confusing, right? I mean, what are these constraints? These are different from unitarity constraints, is that?
Yeah, these are definitely different from unitarity constraints. I don't have an intuition as to where they arise from. At the moment, I should say that it's not very clear how seriously we must take these constraints. It's possible we should. I still don't know what happens when loop corrections are introduced.
No. I mean, at tree level, one can just ask. I mean, Jacobi identity is a mathematical statement, right? It's not some. Right. I'm a bit like if you write down let's say W as operators and then you say it's commutative such and such, then what does it mean to say if Jacobi identity is violated? I think that can only mean that W is probably not an operator or something, or its product is not associative or some.
It probably just means that this is not a symmetry of the theory.
This I don't understand, because I mean it may not be generators. Okay, so W might not be generators and so on, but if you just take any operators and you write A comma B equal to C, I mean, even if they are not symmetry generators, they should be Jacobi, right? I mean, or am I wrong? Like, I understand this point of view that probably the W symmetry is broken or deformed or something, but unless you have a really funny product on the operator algebra, how can you violate Jacobi?
Yoga, can I just add?
Yes.
Yeah. So the way he has constructed these W's, the non-satisfied. I mean, if the corresponding Jacobi is not satisfied, then it would mean that those currents, the way it has been defined, is not a symmetry in presence of the higher derivative term. That is what I would think that it would be.
Now, my question is just simple. Whatever way they're defined, W is defined in some way. And if its commutator is calculated, it should obey Jacobi, right? What does it have to do with that being a symmetry? This is what I don't get.
No, but if it is a symmetry, and if that, I mean, if that is satisfying a particular algebra, then that algebra has to satisfy Jacobi also, no?
Even if it is not a symmetry, I would say Jacobi should be satisfied.
Loga, I think that, sorry.
Loga, I think this is not, you're right, of course, but this commutator is not defined by taking W as an operator, I think, but you are giving a prescription using the OPE to define this commutator. So yeah, it is a priori not obvious they will satisfy Jacobi. It's not, as you are saying, it is not.
Yeah, so exactly. I think the point is whether it closes on this subset of the this thing. These W's are defined in some particular way at some moments, and the question is whether the OPE closes in associative way on these particular moments of currents.
It depends very heavily on the structure of the OPE.
Okay, so maybe if I just understand these answers, you're saying the OPE might not define an associative product on this.
OPE restricted to these currents.
Yes, I think. Currents might not define an associative product, and that's what one is checking. These are the constraints that it is associated. Is that?
I think so. Yeah. Because
in fact, sorry, just I think I would say that even if these constraints are satisfied, there is a prescription, right, Akshay? That I mean, if you had if you were not in MHV setting and you had both holomorphic and anti-holomorphic poles, then I think in general your choice of contour to define this OP would tell you that the Jacobi is satisfied or not, right? I mean, is that?
Yeah, in general, because we have both a holomorphic and anti-holomorphic, we are specifically picking only the holomorphic poles.
Yeah.
So yeah.
If you choose some arbitrary contour, you probably won't even have the Jacobi even then, right?
If we mix the holomorphic and anti-holomorphic, then it definitely does not satisfy. Even even without higher derivative corrections, even then it's not satisfied. Yeah.
Okay.
Alok, did you ask your question?
Yeah. So hi Akshay. So one question I had was that in the old Strominger story, there was a relation between the two soft currents, right? The positive and negative helicity soft currents were not independent because there was a linear combination which decoupled from the S matrix. Right. This gravity, these are the CK constraints.
Yes.
So I just miss, I mean, that should be true here also, right? That the leading soft gluon currents and soft graviton currents are not, for the two helicities, they are not independent of each other. Was that constraint, is it implicit or something we have to impose additionally?
You mean the decoupling of the null states?
I don't know this very well. I mean, I'm saying from the perspective of the soft theorem, remember that the two soft gluons or soft gravitons are not linearly independent. There's a linear combination which decouples from the S matrix, right? I mean, there is one word identity, but two soft theorems, but that just tells us that the two soft theorems are not linearly independent. So maybe
right.
Yeah.
I haven't. I'm not sure how to check that in.
Okay.
Here, because we specifically, the prescription we have is such that, for example, if you were to compute the commutator of two W's with negative helicities, it just vanishes because we are not picking out the anti-holomorphic pole at all.
I see. Okay. Abhijit, sorry, just one small question can I ask? Just
okay.
Yeah. So Akshay, so your collinear factorization was, as far as I understand, was kind of key, right, to derive these OPs.
Yeah.
I mean, if you go beyond tree level, we know that, like in QCD, we know that collinear factorization is violated because of this presence of this what are called Glauber gluons, right? So I don't know. I know you have not looked at loops, but is there any thought? What if the collinear factorization was not valid? I mean, which we know is true in QCD, for example. How this OPs will be defined? I mean, this is a very general question. Just if you had.
Yeah, I haven't thought about it. Actually, even at loop level, we were trying to think about how to even define single soft factors, because these mode expansions are not valid once we introduce log corrections. So we haven't thought about this yet, we have not made any progress.
Yeah, I think we should postpone the rest of the questions to the discussion session. So let's welcome the next speaker now. Akshay, if you could unshare your screen.
Abhijit, sorry, I just want to point out that today's discussion session is going to be a little different from the ones we've had. It seems Subrat is going to lead a discussion on a topic.
Oh, that's right. That is
so
correct.
Perhaps that could be factored in.
So let's have a couple more questions. Two more questions. I guess Somdatta and then Rajesh, and then we will move on to the next speaker.
Yeah. So could you go back to the slide where you define the Mellin transform?
Sure. Here. Okay.
Yeah. So, yeah. So the point of defining the Mellin transform, I guess, was to see how a conformal field theory dual could arise, right? Because that's how you got the deltas and so on, right? Because otherwise,
yeah. The point here is that omega picks up this rescaling factor. So if I were to just look at these states, they don't transform nicely. But here I can just redefine omega and pull out this factor. And I couldn't identify omega with a conformal dimension, but here I could identify it with a conformal dimension because it doesn't change under the conformal transformation.
Yeah. So the whole point is to try to reformulate it in terms of some conformal field theory. That is why you are doing it, right?
Yeah, we're changing the basis of scattering amplitudes and rewriting them in this new basis so that they look like conformal correlation functions.
So my question is, like, maybe you don't try to define the boundary theory, the celestial theory, as a conformal field theory, but just as some plain old field theory, and try to see what happens. Because once you can you go to the next slide?
Yeah.
The next one. Yeah. So because of defining it as a conformal field theory, you are getting these delta z's, right? And that was the problem. So if you instead of defining it as a conformal field theory, if you just left it in terms of the omegas, maybe you
sorry, Somdatta, I think it's better if you give the suggestion to the speaker over the email. We'll go to the next question. Rajesh, please.
Hi. So thanks for a clear talk. I was just wondering, the W infinity algebras come in a one parameter family, the so-called W infinity of lambda, where lambda can be a complex number in general. And the W1 plus infinity that you mentioned of Strominger and so on is a specific point, probably lambda equal to 0 or lambda equal to 1. These are actually the only points, more or less, where the algebra is a kind of a conventional Lie algebra. At any other value of lambda, so even infinitesimally away from the free fermion, free boson W infinity algebras, the algebra is nonlinear in the sense that there are product currents appearing on the right-hand side. And that's necessary for the closure of the whole algebra. So I was just wondering whether maybe there are subtle terms involving products of currents, which maybe you have not yet seen, which are perhaps what might be important for closing the algebra. In fact, I would imagine that's the most natural deformation of the W infinity algebra away from the Einstein gravity point, because the rest cannot be W infinities in a conventional sense, or they must be related to it by a field redefinition if you have a linear algebra. I was wondering you had any thoughts or comments.
Yeah, the initial thought was the little W infinity would get deformed to the well-known big W infinities on when we introduce these corrections. But I guess the fundamental difference there was the way that was derived was we have a bunch of modifications to the little W infinity and we demand closure. but we also demand that the algebra, that we demand this sort of a truncation, and that uniquely fixed that to be a one parameter family. But here we are naturally setting the coupling constants of involving higher spin massless particles to 0. So somehow maybe that it evades the, this is still not very clear to me, but it's possible that it evades the one parameter deformation rule.
So are you saying that the higher spin currents here will be, it will not be sort of, there'll be a proliferation of higher spin currents? Because I thought the usual W infinity of lambda is just based on the fact that, let's say the simplest case, you have one higher spin current for each spin, and then you consider its moments. And I thought if you have that tower, then more or less it's kind of unique to this the same, but there might be loopholes I'm missing.
So I think the point was that the commutator of two of these higher spins involved, they started off with an ansatz. The commutator of these two W's involved a sum of W's of lower spins, and unless the coefficients appearing on the commutator impose the truncation, you would end up with these currents with negative spins. So the coefficients were engineered to specifically produce zeros, and I think that is why you have these 3f4 hypergeometric functions in the big W infinity. But here, just the absence of the higher spin. Here, when I'm saying spin, I mean the usual Minkowski spin. The higher spin massless particles, just having them to be 0 somehow evades this.
Mm-hmm.
So actually, if you look at the structure of the algebra we found, this polynomial n is one factor which appears in the big W infinity, but the big W infinity is also multiplied by a hypergeometric function which is absent here. So yeah.
Okay. All right. Thanks.
Okay. Thank you, Akshay. Let's now have Koushik share his screen.